Since we're discussing standard deviations and regressions to the mean this week, I thought I'd take a moment to describe one of the ways that you may find these data useful. For some of you, this may be review, but you can still see how the description of standard deviations starts to provide some understanding of the story of a population, a sample, or even an individual. There are a number of instruments that use standard scoring in some form. They're often referred to as standardized tests. These tests are typically built upon humongous samples. Some examples of standardized tests might be intelligence tests, or aptitude or ability tests. The ACT and the SAT and the GRE are examples of tests that have been standardized. For this demonstration, I'll ignore college entrance exams. They each use slightly different ways of demonstrating probabilities in the actual score. And instead, we'll use IQ or achievement tests for our example. There is a magical unicorn called a normal distribution. Actually, normal distributions exist in real life, but this is the statistical dream scenario where the greatest probabilities regress toward the mean, and the scores that are far away from the mean are less likely. Also, this magical unicorn has two tails that are the same length, not too long, and a hump in the back, not too high and not too low. It looks like this, the normal distribution. It is the idyllic norm. We'll later ask questions about whether a sample is closer or further away from this norm, but we almost never get this kind of curve. The theory is that the more representative a sample is of the population, the more the sample will represent a normal distribution. If we did get an IQ for every person on the globe, most folks would score near the mean and fewer would be extremely high or extremely low. You can see the standard deviations represented here on the bell curve. Those should look familiar now that you've read the chapters and seen the other videos. In the unicorn scenario, about 68.26% of a population would score between -1 and +1 standard deviations from the mean. 95% of us would score between -1.96 and +1.96 standard deviations from the mean, and 99% of us would score between -2.58 and +2.58 standard deviations from the mean. But it's clunky to say standard deviations from the mean. In this slide, I've added another layer at the bottom. This is how many psychoeducational assessments represent the data. The score of 100 is adjusted to the highest probability. If you have an IQ of 100 and you only associate with people who have your own IQ score, you'd have more friends than anyone else. If, however, you have an IQ of 160 and you refuse to be friends with anyone who doesn't have your exact score, you'd be a very lonely person. In this scenario, 100 is average, and each standard deviation is represented by 15 points on the scale. So if I had an IQ that was 70, it would be 2 standard deviations below the mean, and my IQ would be as good or better than about 2.3% of the population. So who cares? Well, the real advantage of these standard scores is that we can talk about the scores in standard ways without referencing standard deviations. For example, one of the diagnostic criteria for learning disabilities is a standard deviations difference between IQ and achievement. So, if I have an IQ of 100 and an achievement score in math of 84, that difference is bigger than 1 standard deviation. So as you can see, one of the benefits of discussing standard deviations is that it helps us determine whether differences are meaningful. There's not a significant or meaningful difference between an IQ score of 95 and 105. They're within 1 standard deviation from one another. But standard deviations or z-scores or even standard scores will help us start to see differences in probability, and that can be very helpful when we're trying to decide whether those differences are meaningful or significant.